Welcome, everyone. So we are still on chapter 4. We're going to continue 4.3. The objectives are going over methods of proofs and disprove. Very well. So let's review a little bit what we learned so far. Review. We start talking about different types of statements and different methods of proof and disprove for them. Suppose we have an existential statement. Existential statement. If we want to prove an existential statement, to prove an existential statement, we only need to come up with one specific example. So if the question, if the theorem, if the proposal, or in general, a question asks us to prove an existential statement, we come up with one specific example. One specific example. One element, one number, one object is enough for us. For example, in this case, suppose we have this existential statement. It says there is a real number, x, belongs to domain R, such that x plus 5 is equal to 0. Well, okay. By solving this equation, I can find that specific example, that specific object, in this case, that specific number, and I'm done. If the existential statement is about disproving that statement, disprove, well, it means that we are dealing with the negation of existential statement. The negation of existential statement. In chapter 3, we learned about this. The negation of existential statement. Our x belongs to domain D, and we have a predicate, for example, P of x. This is equivalent to saying that the negation of existential quantifier is going to be a universal quantifier. Universal quantifier, x in domain D, such that not P of x. The negation of P of x. So it means that to disprove an existential statement, we need to find and a variable which is arbitrarily, randomly taken from D that satisfies the negation of the predicate. For example, suppose this statement is given to you. There is a real number, like x, such that x squared is negative. Okay, it says, hey, we can find one real number such that if I square it, the outcome is negative. So to disprove this statement, we need to take an arbitrarily taken or randomly taken variable, element like x, such that not P of x. For universal statement, we either try to prove or disprove. If it is about the proof, we have two scenarios. If the domain is finite, we use the method of exhaustion by checking each element in the domain. If the domain is finite. We check each element, each member in the domain. Otherwise, one of the methods that we learn is direct proof with definition. Otherwise, we use direct proof by using the definition. What if we want to disprove a universal statement? Okay, disprove. Okay, to disprove a universal statement, it is equivalent to negating a universal statement. The negation of universal statement, suppose you have for any x in domain D, the predicate P of x. Very well. We know that the negation of universal is existential quantifier. So this is equal to, there is an element in domain D such that not P of x. So we are looking for a specific example, which we call counter example. Specific example, which we call counter example. Well, sometimes you have to use indirect proof. Indirect proof one of them is proof by contradiction. And the other one is called proof by contraposition. Contraposition. In chapter 5, we're going to introduce a new method using induction. So chapter 5, induction. Before writing down the example, let us go over one definition that we went over on Monday, divisibility. Well, suppose you have two integers. Let n and d be integers, with the condition that d is non-zero. D is not zero. Remember that we say that d divides n. We use this vertical line to show that we have divisibility, divides n, if and only if there is another integer like k, such that n is equal to k times d. So we say d is a factor of n, d divides n. N is a multiple of d. It's a multiple of d. N is divisible by d. By d. If and only if you can find an integer like k such that n is d times k or k times d. Here you have multiplication. We can switch in between these two. In page 1, we have this example. The example says, which ones are true? Which ones are true? Very well. Let's write down these. A says, well, 3 divides 21. B, 5 divides 40. C, 7 divides 42. 7. D, negative 16. A negative number divides 32, a positive number. E, 6 is a factor of 54. And F, 7 is a factor of negative 7. A positive number is a factor of negative number. So which ones are true? So take a look at the definition of divisibility. D divides n if and only if we can find one integer such that n can be written as the multiplication of that integer and d. So of course we can write 21 as 3 times 7. We found that integer, which is 7. So the first one is true. How about 40? 40 can be written as 5 times 8. Okay, we found that integer. So using the definition, we're done. 42 can be written as 7 times 6. Okay, 32. 32 is minus 16. You have a negative number times negative 2. So negative times negative gives you positive, of course. Why not? Take a look at the definition. There is an integer. It doesn't specify to be positive or negative. It just says an integer. We found it. It's just right here. And also note that we can write it as 16 times 2. So you can say that, hey, 16 also divides 32. What about this case? 54 is equal to 6 times 9. And here, we say D divides N if and only if we can find that integer K. What is that integer? It is minus 1. We found it. It's just right here. So note that 7 divides minus 7, and the negative number also divides 7 as well. So let us move on to the second page. Page 2. So here we have a theorem. So as theorem says, suppose you have integers a and b, and they are positive. So let a and b be positive integers. A divides B, if A is a factor of B, then the conclusion is that A is less than equals to B. Okay, perfect. So what do we have here? We have a hypothesis that says A and B are positive integers, and we also know that A divides B. What is the goal? The goal is to show that A is less than equals to B. So this is the conclusion that we try to prove. We're not looking for a specific example here. We're trying to prove a universal statement. To prove this universal statement, let us try using direct proof. So our goal is to show that A is less than equals to B. What are we going to do? We're going to use all the assumptions that we have, combine them together, and get to this conclusion. Very well. What I'm going to do, I'm going to start by using the divisibility. Since A divides B, by definition, there exists an integer like K such that B is equal to A times K. I'm going to put this guy in a little box. This is important for me. I'm going to later use it. Using the first assumption here for divisibility. I also have another assumption. It says they are positive integers. A and B are positive. What is our conclusion about K? Can K be negative? K cannot be negative. If K is negative, A, we know that it's positive, and negative times positive is going to be negative, which has contradiction with the assumption that we have. So since A and B are positive, so K is also positive. K is an integer, which is positive, so it takes on values starting from 1. So K is greater than or equal to 1. Now I'm going to multiply both sides by A. I'm going to multiply both sides by A because I know B is equal to A times K. At the same time, A is positive. It doesn't change the inequality. So let us multiply both sides by A. So I get A less than equals to K times A, or A times K. So take a look at your box. B is equal to the product between A and K. This is equal to, well, I just showed that A is less than equals to B, which is the conclusion that I was trying to reach. So we're done with our proof. We're moving on to our next theorem. Well, this theorem says 1 has 2 factors, and these 2 are the only factors for 1. Theorem. The only factors of 1 are 1 and -1. So 1 has only 2 factors, and our goal is to prove that. What's the proof like? Well, let's say, hey, we can write 1 as 1 times 1. N is equal to D times K. So 1 divides 1. Or you might say, hey, 1 can be written as the product of -1 and -1. Of course, why not? -1 times -1 is equal to 1. So N can be written as D times K. In both cases, we just show that 1 divides 1 and -1 divides 1. Well, is that enough? Am I done with the proof? Take a look at your theorem. It says the only factors. So what's the meaning of that? It means that if I randomly select an integer, and that integer is a factor of 1, that integer is either 1 or negative. That's the meaning of that. Now, we need to show that. For an integer like m, such that m divides 1, m is equal to 1, or m is equal to -1. So let us add in here. M divides 1, then m is equal to 1, or m is equal to -1. I'm going to use the theorem that I just proved for you. So let's see. M divides 1. What's the meaning of that? By using divisibility, m divides 1 if and only if there exists another integer like k such that 1 is equal to m times k. M is just an integer. This integer can be positive, it can be negative, all right? So suppose m is positive. If m is positive, then m times k is equal to 1. M times k is equal to 1. Okay. Take a look at this theorem. This theorem says if m divides 1 and these two numbers are both positive, then m is less than equals to 1. Since m is positive, the previous theorem says, well, this m must be less than equals to 1. You have a positive integer which is less than equals to 1. What is that integer? That integer is nothing but 1. So m is 1. So if we have an integer like m that divides 1, and if it's positive, it's nothing but 1. What if m is negative? M is negative. If m is negative, then minus m is a positive number. So negative m is positive. Well, I know m times k is equal to 1 minus m times minus k is also 1. What's the meaning of that? It means that negative m as a positive number divides 1. Let's get back to the theorem. Negative m, which is a positive number, divides 1. So negative m is less than equals to 1. Again, my previous theorem, negative m is less than equals to 1. A positive number, which is less than equals to 1, it means that negative m is nothing but 1, or m is minus 1. We're done with our proof. Example for you. So we are on page 3. This example says, well, so let's write down part A first. It says, let A and B be integers. So if A and B are integers, then 3 divides 3A plus 3B. Is this true? Is this false? Well, 3 divides 3A plus 3B. So first of all, we can write 3A plus 3B equals to. In algebra, we learned that if we factor out 3, we end up with A plus B. What is A? What is B? Those are just integers. The sum of 2 integers is an integer. So we have 3 times an integer. 3 is a factor of this number. So 3 divides 3 times A plus B. Equivalently, if you distribute 3 divides 3A plus 3. How about this example? If K and M are integers, then can we conclude that 5 divides 10K times M? Let's run this. So since 10 times Km can be written as 5 times 2 times Km, we can group these two together. The multiplication of 2 integers is an integer. 2 times that integer is also an integer. So you have 5 times an integer. Do we see factor 5? Yes, of course. 5 is just right here. What's the meaning of that? It means that 5 divides 5 times its integer, 2Km. So 5 divides 10 times K times M. So both answers are yes. Here's a question. was 4 divide 15. Is 4 a factor of 15? The answer, as you know, is no. Well, here's a note for you. We say that D doesn't divide N if and only if when you do the division N divided by D, the outcome is not an integer. Means that the division has a remainder. The remainder is non-zero. You can say that, hey, 15 divided by 4, it's not an integer, therefore 4 doesn't divide 15. Another note for you. We can't define a prime number, an integer, like n is prime if and only if. First of all, that number must be absolutely greater than 1. And if n can be written as the product of 2 other integers, like r and s are 2 integers, then we have n equals to r or n is equal to s. We can use the definition of divisibility to rewrite the prime number definition by using divisibility. We say that a number is prime, an integer, like n is prime if and only if n is greater than 1 and its factors are 1 and n. Alternate way to define a prime number. So let's move on to the next page. Page 4. Transitive property for divisibility. Theorem. Okay. Very well. Suppose you have integers. Let A, B, and C be integers. If A is a factor of B and B is a factor of C, then the conclusion is A is a factor of C. A divides C. Proof. As you can see, here you have a universal statement. So specific examples, they don't work here. Proof, we're going to use direct proof by definition. Okay, what are the assumptions here? We know A divides B. Let us use that first. A divides B by definition. There is an integer like K such that B is equal to A times K. this guy in a box and number it 1. The second part says B also divides C. Okay. B is a factor of C. Again, using the definition. By definition, there is an integer. Let us use L. L such that C can be written as L times B or B times. Well, I'm going to put this one in a box as well. Number 2. Okay, take a look at these two boxes here. I know from box 1 that B is A times K. So I have B just right here. And in the second box, I also have B. Just substitute that. So by substitution of 1 into 2, we have C equals to A times K times L. I'm going to group these two together, K and L. The multiplication of two integers is an integer. So here you have your integer. Well, but what is this? This is nothing but the definition of divisibility. It says A is a factor of C. So A divides C, which was the conclusion I was trying to prove. So we're done with this proof. If A and B have the following conditions, if A divides B and B divides A, can we conclude that they are equal to each other? I'm going to tell you that this is not true. Why is that? At the beginning of lecture, I gave you an example. I said -7 divides 7, and also 7 divides -7. A divides B, B divides A. Are they equal to each other? Of course not. So for this universal statement, we can write a counter example. So the answer is no. We have counter example. You can use 2, -2. You can use any other number, and it's opposite here. So suppose A, B, C are integers. This is another example for you. Let A, B, C are integers. And suppose A divides B and A also divides C. A is a factor of C as well. Then the conclusion says, well, A must divide the sum of B and C. Is this true or false? If it's true, how do you prove it? If it's false, what is the counterexample? Well, this statement is true. This is a true statement. Why is that? I'm going to use direct proof, proof by definition, to show that this is true. Very well. What is the hypothesis? It says A divides B. Okay. A divides B by definition of divisibility. By definition, there is an integer like k such that B is A times k. Okay, so let's take a look at the second part of the assumption here. A divides C. Okay, A divides C. Again, by definition, there exists an integer like L such that C is A times L. I'm going to use those boxes that I like to use. I don't want to lose these. So B is equal to AK and C is equal to AL. I'm going to add 1 and 2. Add 1 and 2. B plus C is equal to A parentheses K plus L. Isn't that an integer? Of course. Do you see the factor here? Yes. So A is a factor of B plus C. We're done with our proof here. The joy of proving statements. Very well. Okay, 2 more examples for you. We are still on page 4. I'm going to write the first one on the left-hand side of the board and the second one on the right-hand side of the board. So this guy says, well, suppose A, B, C are integers. Let A, B, C are integers. Okay, it says if AB divides C, then A divides C and also B divides C. Okay. Is it true? Is it false? And another example on page 4 says, well, for all integers like A, B, and C, A, B, C, if A divides B plus C, then A divides B or A divides C. Perfect. So, yeah. Well, so what do we have here? For this guy, the answer is yes. Why it is yes? Okay, let's just try to prove it. Proof. Universal statement, try to use direct proof, proof by definition. What do we have here? We have an assumption. The assumption says, hey, AB is a factor of C. AB divides C. By definition of divisibility, there exists an integer like K such that C is K times AB. Well, I'm going to rewrite this guy in 2 different formats. C can be written as K times B times A. So you have A times an integer So A divides C. So A divides C. I can also write C as K times A, group these two together, times B, another integer. All right. Okay. Well, integer. So by using the definition of divisibility, B also divides C. We're done without proof. Okay. The answer to this example is no. No. Why? Because we can find counter example. We can find counter example. So think about it this way. 2 is a factor of 4. This is true, of course. 4 can be written as 1 plus 3. So B is 1, C is 3. But 2 doesn't divide 1. 2 doesn't divide 3. So can use tons of different counter examples here. Well, what is the factorization of a number? When we're talking about factorization of numbers, you're interested in finding all prime factors for that number. They might have some exponents as well. So the factorization of this number, 3,300. This guy can be written as 33 times 100, which is 3 times 11 times 4 times 25, which is 3 times 11 times 2 squared times 5 squared. So this is the factorization of this number into primes. If I rearrange this based on the prime numbers, I get a standard form. Standard factorization. So this number can be written as, well, 2 squared times 3 times 5 squared times 11. It happens that we can factor out any number, any integer greater than 1. So any integer like n greater than 1 has a unique prime factorization. This can be written this way. N is equal to p sub 1 raised to exponent p1. P sub 2 raised to exponent p sub 2. P sub 3 raised to e sub 3, and the rest we stop at some point. P sub k raised to e sub k. P1, P2, P3, Pk, those are prime numbers. P1 is different from P2, is different from P3, is different from Pk, are primes. E1, E2, E3, E4, Ek, those are just integers, exponents. So E1, E2, they might be equal to each other, they might be not equal to each other. E3 to EK are positive integers. So if you have any integer like n, there is absolutely prime factorization available for that number. Question for you. So this question says, suppose m is an integer. Let m be an integer. And 8 times 7 times 6 times m. Stop here. Is equal to 17 times 16 dot 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 up to 10. Does 17 divide m? Can we say that 17 is a factor of m? Very well. The answer here is yes. Yes. Why is that? So don't overthink it. What do you have on the right-hand side? On the right-hand side, you have a number including 17. So, of course, 17 divides this number here. So 17 divides any number including 17. So 17 times 16 times 15 up to 10. You know that. So this is your right-hand side. Right-hand side. And this is your left-hand side. 17 divides right-hand side. Right-hand side and left-hand side are equal to each other. So 17 must divide left-hand side. Left-hand side, which is nothing but 8 times 7 times 6 times, here we have our m, times 5, 4, 3, 2, and let me just move this a little bit here. Need more space. So again, 17 divides right-hand side, which is 17, times 16, dot, 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 10, which is your right-hand side. Right-hand side and left-hand side are equal to each other. So 17 must divide left-hand side as well. 8 times 7 times 6 times 5 times 4 times 3 times 2 times 10, which is our left-hand side. Okay, so let us think about this part. We want to know what is the connection between 17 and m. Well, does the 17 divide 8? 17 doesn't divide 8. Of course, 17 doesn't divide 7. 17 doesn't divide 6. 17 doesn't divide 5. 17 is not a factor here. The only thing that is left is m. 17 doesn't divide 5. 17 doesn't divide 4. 17 doesn't divide 3. 17 doesn't divide 2. So what's left? We know 17 is a factor of this number. So the only thing that is left is m. So 17 must divide